Now, in previous installments of the regional disaster relief scenario, we went through all the basic phases of a line balancing problem. We found the cycle time, drew a precedence diagram, and then actually balanced the line. In this scenario, we are asking questions, and this is all we're doing, is just asking questions about how good a design did we think we found in the previous scenario. Now let's look. In scenario 1C, that's that previous scenario, how much idle time does each workstation experience along the along the overnight kit assembly line? Now, I have our notes from when we actually designed that line, and you'll remember that on a line balancing worksheet, you find the design in the far right hand column. Let's just sketch this again, except from left to right. At the first workstation, this is what we decided. Tasks B and then task A will be performed. Task B, this was just data that was provided, was 60 seconds, and task A was 30 seconds. All of this represents the first workstation in that design. Now idle time. How much idle time is actually enjoyed, so to speak, at that workstation? Idle time is the cycle time, the total budget of time that the workstation is given to do something, minus the amount of time that it actually takes for the workstation to do whatever was assigned to it. So we have to recall that way back at the beginning of this, we discovered that the cycle time that this assembly line needs to use to operate was 90 seconds. So each time a workstation does whatever it's assigned to it, it will have 90 seconds. Now wait, at the first workstation it'll have 90 seconds. 90 seconds minus, wait a minute, 60 plus 30 is 90 seconds worth of work? Say, well, that's nothing. Right, zero idle time at the first workstation. Now, at the second workstation, things were a little bit more complicated. If you look back at the original scenario, at the second workstation, there were 3 tasks assigned. Task C, Task F, and Task G. That's what we decided. Now C is 45 seconds long. F is 30 seconds long. And G was real short. G was 10 seconds long. So that is what the second workstation will be doing over and over again. You say, all right, well, how much idle time do they enjoy each cycle? They have the same 90 seconds that all the other workstations have to do their work. We say, all right, 45 plus 30 is 75, plus 10 is 85. They have 85 seconds worth of work. Wow. Each cycle, they enjoy a whole 5 seconds of idle time. The third workstation also has 3 things assigned to it. Let's see, we had decided that it would do D, E, and H, those 3 tasks. Now I'm looking upon the data, how long they actually take. D was pretty long, 60 seconds. E was only 20 seconds, and H was 10 seconds. We decided this when we did the line balancing. And you say, all right, well, idle. 90 seconds is what they have to work with. That's the cycle time. 60 plus 20 plus 10 is 90. Here is another workstation with no idle time. And then over here, I'm going to have to squeeze it into my illustration because we squoze, so to speak, one last workstation onto our line. The fourth workstation only did task I, which is only 60 seconds long. So at that workstation, they have 90 seconds. It's the same 90 seconds the other workstations have. There's only 60 seconds worth of work to do. So if we were speaking about the relative load on the 4 workstations that we created in our design, we would very naturally say that, oh, it's the 4th workstation or the last workstation that has the most idle time. It has 30 seconds of idle time. The 1st workstation and the 3rd workstation don't have any idle time at all. I'm wondering if, now that we did that longhand, if from working on that line balancing sheet in the previous scenario, if that pattern of 0, 5, 0, and 30 seemed familiar. If you know where to look for it, you actually don't have to do those calculations separately. If you've done the line balancing problem, this is the line balancing problem itself. This is what it looks like. Do you notice 0, 5, 0, and 30? These are the idle times. Yes, you find the idle time in your line balancing worksheet. It is that one last number under time remaining when you gave up on that station and drew a line under it and said, fine, I'm opening another workstation. It might be 0. You might have used the cycle time up completely, or it might be an odd number like 5 or 30 because you couldn't find any eligible tasks that would fit in that number. That actually is the idle time. Oh, so that's good. It's a good shortcut to calculating idle time if you know where to look for it. Now there are some other kind of follow-up questions in this scenario. This question here, it says, how efficient is the design? Talking about this design we've been looking at. Oh, efficiency is a good quick calculation that you can make on behalf of any design. You just have to know how to fill in this ratio. Now, ST stands for sum of tasks. That number right there. You say sum of tasks. What's that supposed to be? Oh, easy. That is 60 plus 30 plus 45 plus 30 plus 10 plus 60 plus 20 plus 10 plus 60. The sum of tasks is there are these original tasks that you were trying to assign to stations. Just add up the total amount of work that's there. I did that. 60 plus 30 plus 45 plus 30 plus 10 plus 60 plus 20 plus 10 plus 60. That's all the numerator. Now, that is a familiar abbreviation right there. That is the cycle time. Oh, which in our case, down here, my scratch work is 90. And it says cycle times n. N equals number of workstations. Number of workstations, yeah, just when you were done with your design, how many of them actually were there? Well, in our case, there was 4. So on my calculator, I get 0.9028. Add all that up, divide by, what's it, 360, 90 times 4, 0.9028. What's that supposed to mean? Oh, basically 90%. To answer the question, the design that we produced in this scenario, it's basically 90% efficient. Okay. Now, do you notice the question that comes after that? What is the balance delay in this design? If you found efficiency, balance delay is really easy to find because it is nothing more than the opposite of efficiency. 1 minus the efficiency, or in our case, 1 minus that 0.9028, which is 0.0972, or basically 10%. Yeah, I'm just doing some rounding for the percent. Right. If it's 90% efficient, we would say if a design's 90% efficient, oh, it has a 10% balance delay. They're just complements of each other. It's just a performance rating. Okay. Now, the bottom of the page actually scrolls in just above the footer. It says, is this a good design? I don't know. We don't have anything to compare it to. We don't have an alternate design to compare it to. Actually, the 90% sounds pretty good. It does. We just don't know if maybe if we used a different decision rule to kind of mix up the distribution of tasks across the workstation, maybe we could get an even higher efficiency, because that's what you'd be looking for, a higher efficiency than that. We don't know at this point, although nothing to compare it to. Use different rules. Can you find a better design? I'm thinking with 90% efficiency, we probably have to be at least pretty close, but we don't know.